The S-400 Triumf entered service in 2007 with a singular promise: to render Western air superiority obsolete. Russian military doctrine didn't frame it as another air defense system. They positioned it as the algorithmic endpoint of aerial warfare. The specifications read like a threat matrix: 400-kilometer engagement range, simultaneous tracking of 300 targets, engagement of 36, the 4ON-6E missile, a hypersonic interceptor capable of destroying aircraft at altitudes approaching near space. On paper, the S-400 represented layered lethality: X-band engagement radars, S-band acquisition arrays, and data link architecture that could theoretically coordinate across an integrated air defense network spanning hundreds of kilometers. Export customers lined up: Turkey, India, China, Saudi Arabia. And the procurement wasn't purely transactional, it was symbolic. Purchasing the S-400 meant buying into a narrative that Russian computational warfare had leapfrogged NATO's kinetic advantage. But to understand the myth, you must understand the engineering. The S-400 is not a single weapon, it's a kill web. At its foundation sits the 91N6E Big Bird radar, a massive S-band phased array capable of detecting targets at ranges exceeding 600 kilometers. This is the Sentinel, the watcher that never sleeps. Above it, in the electromagnetic spectrum, operates the 96L6E acquisition radar, X-band. Higher frequency, shorter wavelength. This is the Hunter. Where the Big Bird sees the battlefield, the 96L6E refines individual targets, measuring their velocity vectors, discriminating between aircraft and missiles, filtering clutter from the ground return. Almaz-antey's engineers didn't just build radars, they built a cognitive system. The tracking algorithms employ Kalman filtering, a mathematical technique that predicts where a target will be based on where it's been. If an aircraft maneuvers, the filter adapts. If chaff blooms, the Doppler processors ignore it. If a target attempts terrain masking, the look-down, shoot-down capability isolates the moving signature from static background. The system was designed to hunt the F-35, specifically. The Joint Strike Fighter's reduced radar cross-section, estimated at 0.0015 square meters from certain aspects, was the benchmark. Russian engineers assumed that if the S-400 could reliably track and engage a fifth-generation stealth platform, everything else in NATO's inventory would be trivial, so they built redundancy into every layer. The S-400 doesn't rely on a single radar band. It fuses data from L-band, S-band, and X-band emitters. L-band wavelengths, longer, lower resolution, can detect the basic presence of stealth aircraft because their shaping is optimized against shorter wavelengths. S-band provides the initial track. X-band delivers the precision needed for a kill. The fire control architecture incorporates automatic target classification. The system doesn't just see a return, it analyzes the radar signature, compares it against a library of known profiles, and determines fighter, bomber, cruise missile, drone. Each classification triggers a specific engagement protocol, each protocol optimized through decades of telemetry data and combat modeling. And then there's the cross-polarization capability. Modern stealth aircraft use radar-absorbent materials that work by converting electromagnetic energy into heat. But conversion isn't perfect. Some energy reflects back, often with altered polarization. The S-400's receivers are tuned to detect these polarization shifts, subtle indicators that a target is employing absorption techniques rather than passive deflection. By 2025, Russian defense analysts had stopped calling the S-400 a weapon. They called it a filter, a computational barrier that separated serious air forces from historical ones. The psychological dimension mattered as much as the technical. When Turkey purchased the S-400 in 2017, the United States responded by ejecting Ankara from the F-35 program. The message was clear. You cannot operate both systems. The S-400 was treated not as hardware, but as a doctrinal infection. NATO couldn't risk the possibility that Turkish S-400 operators might collect emission signatures from F-35s during joint exercises. This fear validated the myth. If the Americans were terrified of the S-400 learning the F-35's signature, then surely the S-400 was invincible. But myths are built on assumptions. The S-400's designers assumed rational adversaries. They assumed aircraft would behave according to aerodynamic laws. They assumed radar returns would correspond to physical objects moving through three-dimensional space at velocities consistent with thrust-to-weight ratios and drag coefficients. They assumed fundamentally that the electromagnetic spectrum was a domain of truth, that radar returns represented reality, filtered through atmosphere and clutter, but fundamentally honest. The assumption was mathematical. No subsonic platform could penetrate. No legacy airframe could survive. No amount of pilot skill could overcome algorithmic certainty. That assumption held until March 2026. The Fairchild Republic. A-10 Thunderbolt II is not a solution in search of a problem. It is a problem that refuses to die. First flight, 1972. Operational deployment, 1977. The airframe was designed during an era when the Pentagon genuinely believed the next European war would be fought with massed Soviet tank columns pouring through the Fulda Gap. The A-10 wasn't built for elegance. It was built around a single instrument, the GAU-8/A Avenger, a 7-barrel rotary cannon that fires 30mm depleted uranium rounds at 3,900 rounds per minute. Everything else, the titanium bathtub protecting the pilot, the redundant hydraulic systems, the straight-wing design optimized for low-speed loitering, was subordinate to that gun. By any rational metric, the A-10 should have been retired decades ago. Maximum speed, 381 knots. Service ceiling, 45,000 feet. Radar cross-section, approximately 23.5 square meters. To put that in perspective, an F-35's RCS is estimated at 0.0015 square meters. The A-10 is not stealthy. It is, electromagnetically speaking, a barn door. But in late 2025, the 354th Fighter Squadron at Davis-Monthan Air Force Base began flight testing a modification that didn't appear in any press release. The designation was prosaic. AN/ALQ-260 Integrated Defensive Electronic Countermeasures POD. Cost per unit, approximately $2.3 million. Weight, 187 kilograms. The pod's function was not passive radar absorption. It was active waveform manipulation. To understand what the ALQ-260 does, you must understand what radar actually is. A radar transmits electromagnetic pulses, photons fundamentally, and measures the time delay of their return. That delay corresponds to distance. The Doppler shift of the reflected wave corresponds to velocity. The amplitude and phase of the return correspond to the target's size and aspect. All of this happens at the speed of light. A pulse travels to the target and back in microseconds. The radar's processor expects a specific relationship between transmission and reception. Pulse repetition frequency. Modulation pattern. Phase coherence. The ALQ-260 breaks that expectation. Inside the pod is a digital radio frequency memory system. When the S-400's engagement radar illuminates the A-10, the DRFM doesn't absorb the pulse, it captures it. Or the incoming waveform is sampled at gigahertz rates, converted from analog to digital, stored in high-speed memory, modified, and retransmitted, all within nanoseconds. The radar doesn't receive a simple echo. It receives a synthetic construction. The DRFM can time-shift the return, making the aircraft appear closer or farther than it actually is. This is range gate pull-off. The tracking algorithm expects the target to move smoothly through space. Instead, it jumps. The range gate, a narrow window of time the radar uses to isolate a specific target, loses lock. But range manipulation alone isn't sufficient. The S-400's processors are designed to handle erratic returns, so the ALQ-260 adds a second layer, velocity gate pull-off. By modulating the Doppler frequency of the retransmitted pulse, the pod makes the A-10 appear to be accelerating or decelerating at rates incompatible with aerodynamics. A subsonic aircraft suddenly shows a closure rate of Mach 2. Then it appears to reverse direction. Then it vanishes from the velocity filter entirely. The tracking algorithm built on Kalman predictions begins to diverge. The filter assumes smooth motion. When motion becomes chaotic, the error covariance explodes. The system doesn't just lose confidence in the track, it questions whether the track ever existed. The third layer is the most insidious, coherent, false target generation. The DRFM doesn't just distort the original return, it fabricates new ones. A single incoming pulse can generate a dozen outgoing responses, each offset slightly in time, frequency, and phase. The radar sees not one aircraft, but a formation. Not a formation, but a cloud. These aren't random ghosts, they're mathematically plausible. Each false return has the correct pulse width, the correct modulation, the correct polarization. The radar's automatic discrimination algorithms, designed to filter noise, can't reject them because they're indistinguishable from real targets, and then there's cross-polarization jamming. The S-400 transmits linearly polarized pulses and expects returns in the same polarization. The ALQ-260 can retransmit in orthogonal polarization, exploiting the fact that the radar's receivers have finite cross-polarization rejection ratios. This degrades signal-to-noise ratio, forcing the processor to lower detection thresholds, which increases false alarm rates, which saturates the tracking queue. But the most sophisticated element is adaptive. The ALQ-260 doesn't just jam, it learns. The pod contains a threat library, known radar modes, pulse repetition frequencies, modulation schemes. When illuminated, it identifies the emitter, selects the optimal countermeasure, and adapts in real time. If the radar frequency hops, the DRFM follows. If the radar switches from pulse Doppler to continuous wave mode, the pod reconfigures its response. None of this makes the A-10 invisible. It makes it unresolvable. And for an automated fire control system dependent on algorithmic certainty, unresolvable is functionally equivalent to absent. The system was never intended for penetration missions. It was developed for survivability in contested environments where the A-10 would operate under friendly air superiority. But in early 2026, someone at Air Combat Command asked a different question. What happens if you don't send one? What happens if you send 50? The answer required a doctrinal shift. Electronic warfare had traditionally been a support function, jamming radars to protect strike packages, degrading communications to isolate enemy formations. But the ALQ-260 enabled a different concept, electronic attack as the primary mission. The A-10S wouldn't need to destroy the S-400 batteries, they would paralyze them, not through kinetic effects but through computational overload. 50 aircraft, 50 DRFM pods, each generating dozens of false targets. The math was brutal. The S-400 network would be attempting to track and correlate potentially thousands of returns, the vast majority synthetic, all coherent enough to pass initial discrimination filters, all moving in patterns designed to maximize computational load on the tracking algorithms. The operation wasn't a test of hardware, it was a stress test of epistemology. Can an algorithm be made to disbelieve its sensors? Can a system designed for certainty function in an environment of manufactured ambiguity? March 2026 would provide the answer. The operation, whether exercise or something more operational, occurred during the second week of March 2026. The location remains contested. Open-source intelligence suggests an area within 200 kilometers of Kaliningrad, a Russian exclave hosting one of the densest concentrations of S-400 batteries in Europe. 50 A-10 Thunderbolt IIs. each configured with the ALQ-260 pod, each carrying a minimal weapons load to reduce drag, each piloted by personnel who had trained in low altitude, so terrain masking ingress profiles for months. The flight plan wasn't innovative, it was Neolithic. The formation approached at 500 feet above ground level, using coastal terrain and the Baltic's natural clutter environment to delay initial detection. Airspeed, 320 knots, spacing, staggered intervals to prevent overlapping radar returns. The first S-400 battery to detect the formation was a 40 V6M mast-mounted search radar stationed near Baltisk. The initial track logged at 4:47 local time. Senior Lieutenant Dmitry Volkov, the duty operator, reported multiple contacts bearing 285 degrees, range 140 kilometers. Track count, 600 plus. Volkov's first assumption was malfunction. 600 aircraft don't simply appear off the Baltic coast. He reported the anomaly to the supervising officer, Major Konstantin Baranov. Your Baranov ordered a system reset. Standard protocol. The radar cycled through its initialization sequence. 30 seconds of blindness. Then reacquisition. The contacts remained. Then doubled. Baranov authorized engagement radar activation. The 91N6E Big Bird radar came online, its phased array sweeping the formation with S-band pulses. It registered 1,200 returns. The target count alone violated tactical logic. NATO doesn't have 1,200 aircraft in theater. NATO doesn't have 1,200 combat aircraft in Europe. But the absurdity extended beyond numbers. The tracking data was statistically impossible. Aircraft separated by fewer than 10 meters, closer than wingtip to wingtip formation flying. Velocities fluctuating between 200 and 600 knots within single scan intervals. Altitudes from sea level to 15,000 feet, to contacts appearing to climb at rates exceeding 50,000 feet per minute. The tracking algorithms attempted correlation. Standard procedure: establish a tentative track, predict forward motion, confirm with subsequent scans. But every time a track solidified, it fragmented. One return became 12. 12 became 60. Velocity vectors pointed in contradictory directions. Range gates pulled open and snapped shut. At 4:52, Baranov made the decision that would define the engagement. He authorized active engagement radar. The 96L6E X-band system illuminated the formation with targeting quality pulses. This was no longer surveillance. This was weapons-grade tracking. The ALQ-260 pods received the illumination. They had been waiting for it. The DRFM system sampled the X-band waveforms, digitized them, and retransmitted. The radar's processor was now receiving not echoes, but synthetic constructs, waveforms indistinguishable from real returns, but corrupted with phase noise, false Doppler, and timing offsets. Inside the command bunker, the fire control display became incomprehensible. Senior Warrant Officer Yuri Petrov, the weapons director, watched the tactical picture disintegrate into chaos. Tracks appeared, disappeared, merged, split. The track correlation algorithm, designed to maintain continuity across scan intervals, was generating error messages. Track divergence exceeded threshold. Velocity discontinuity detected. Range rate inconsistent with target classification. Petrov had 15 years of experience. He'd trained on the S-400 since its introduction to operational units. He'd engaged targets in Syria, drones, cruise missiles, our simulated NATO strike packages and exercises. He'd never seen this. At 4:54, he attempted to authorize a launch. The fire control computer rejected the command. Target solution unstable. Petrov tried manual override. The system allowed it, barely. He designated a track that appeared marginally more coherent than the others. Azimuth, 287 degrees. Elevation 3 degrees. Range 94 kilometers. Velocity 340 knots. The computer calculated an intercept solution and cued a 48 north, 6 east missile. Then the track vanished. Not degraded. Vanished. The range gate showed empty space. 2 seconds later, a return appeared 35 kilometers displaced. Same velocity. Impossible trajectory. Petrov aborted. The missile remained in its tube. The A-10s continued inbound. Major Baranov contacted the Integrated Air Defense Network. A second battery, 22 kilometers south at Primorsk, was cued into the engagement. The theory was triangulation. If both batteries were tracking the same targets, cross-correlation would filter the false returns. Geometry would reveal truth. The Primorsk battery activated its 96L6E. Now 2 X-band radars were illuminating the formation from different aspects. The network fusion algorithm attempted to match tracks between sites. It failed immediately. The ALQ-260 pods had anticipated this. Each DRFM had been pre-programmed with slight timing offsets, microsecond delays that desynchronized the false returns between radar sites. A ghost that appeared at bearing 285 degrees from Baltijsk would appear at 290 degrees from Primorsk. The correlation algorithm expected geometric consistency. It received geometric chaos. Instead of refining the track, the networking multiplied the confusion. Now both batteries were sharing false data, each contaminating the other's picture with synthetic returns that appeared real but couldn't be reconciled. By 0503, the S-400 network had logged over 4,000 discrete tracks. The fire control displays at both Baltijsk and Primorsk were saturated. The automatic targeting queues were full. Priority algorithms were cycling frantically, attempting to identify the highest threat targets. Every candidate was either statistically implausible or geometrically impossible. Baranov made the final decision. He ordered both batteries to disable automatic mode. The engagement would proceed manually. Visual coordination with optical tracking systems. Humans, not algorithms, would make the determination. But at 500 feet above ground level in pre-dawn twilight, against a coastal backdrop, the A-10s were intermittently visible at best. The optical trackers reported fleeting contacts, gray shapes against gray water, visible for seconds before disappearing into ground clutter. At 5:11, the formation turned. They didn't penetrate the defended zone. They didn't need to. They had already accomplished the objective, proving that the S-400's engagement capability could be reduced to 0 without firing a shot. The battery logs recorded 37 attempted target locks, 0 valid launch solutions. Inside the Baltijsk command bunker, Major Baranov sat in silence. His screen still showed thousands of contacts. His missiles remained unfired. His system, the most sophisticated air defense network ever deployed, had been rendered impotent by aircraft designed when his father was a child. The operational debrief would later note a single phrase, attributed to Baranov's report. If there are 4,000 targets, there are no targets. 50 obsolete aircraft. 50 pods. Total modification cost, approximately $115 million. The S-400 battery complex they neutralized, estimated value exceeding $1.2 billion. The incident did not appear in Russian Defense Ministry briefings. It did not generate formal NATO press releases. But within 72 hours, signals intelligence intercepts indicated a classified technical review had been initiated at Almaz-antey, the S-400's manufacturer. The review's conclusions remain internal, but the subsequent actions were observable. Software patches were distributed to deployed batteries within a week. The modifications focused on tightening correlation thresholds and implementing heuristic filters to discard statistically improbable tracks. But the patches addressed symptoms, not architecture. The S-400's tracking algorithms were optimized for an adversary that played by implicit rules. aircraft with predictable radar cross-sections, coherent flight profiles, electronically passive or minimally active signatures. The ALQ-260 didn't break those rules. It deleted them. The broader implication is doctrinal. For 2 decades, Russian air defense strategy has been predicated on computational dominance, the belief that superior algorithms, networked sensors, and adaptive processing could offset NATO's numerical and qualitative advantages in airframes. The S-400 was the flagship of that doctrine. But computational systems have a failure mode that kinetic systems do not. They can be made to doubt themselves. A missile either hits or misses. A gun either fires or jams. But an algorithm can be fed inputs that cause it to reject reality entirely. There's a historical parallel worth noting. In The Prince, Machiavelli warned against reliance on mercenary arms, forces not intrinsically loyal, not bound by organic interest to the sovereign's survival. A mercenary army, he argued, fights only as long as it's profitable. When the battle turns, it abandons the field. An S-400 is a digital mercenary. It defends only as long as its algorithmic confidence remains high. When that confidence is corrupted, when its sensors report a reality it cannot reconcile, it refuses engagement. The sovereign, in this case the Russian integrated air defense network, is left naked. The A-10 operation demonstrated that the cost asymmetry in electronic warfare now favors the attacker. A $2.3 million pod can neutralize a $300 million fire unit. A 50-year-old airframe can render a cutting-edge system impotent, not through technological superiority, but through exploiting the brittleness of over-optimization. The S-400 was designed to kill the F-35, the B-2, the most sophisticated platforms NATO could field. It was not designed to be confused by subsonic trucks carrying smart radios. This is the paradox of algorithmic warfare. The more sophisticated the system, the more precisely it can be deceived. Stealth reduces radar cross-section. Electronic attack doesn't reduce the signature. It manufactures fake ones, exploiting the very sensitivity that makes modern radars effective. Russian defense analysts now face an uncomfortable question. If the S-400 cannot reliably engage modified A-10s, what happens when the same techniques are applied to platforms actually designed for penetration? What happens when B-21s, F-35s, and loyal wingman UCAVs integrate 4th-generation DRFM pods with their existing low observable characteristics? The answer is already being written into updated doctrine. The Russian military has quietly resumed development of optically guided short-range air defense systems, weapons that don't rely on radar at all. Panzer SM units are being retrofitted with enhanced electro-optical trackers. Development funding for laser-based air defense has increased 40% in the 2026 fiscal year. A regression, in a sense. A tacit admission that in some scenarios, the Mark I eyeball remains harder to deceive than a phased array. But the deeper lesson is epistemological. Modern warfare has become a contest not of firepower, but of information dominance. The side that can see accurately, decide rapidly, and act decisively holds the advantage. But what happens when seeing becomes unreliable? When sensors can be made to hallucinate? The S-400 debacle revealed a truth that military planners are reluctant to acknowledge. There is no such thing as perfect information. Every sensor can be spoofed. Every algorithm has edge cases. Every system built on the assumption of computational certainty contains within it the seeds of catastrophic failure. The A-10 was supposed to be obsolete. In a certain sense, it is. But obsolescence has a peculiar property. It can make you invisible to systems designed to see the future. 50 warthogs proved that the most dangerous aircraft isn't the one your radar can't see. It's the one your radar sees everywhere, all at once, and nowhere that matters. Software didn't just eat hardware, it choked on it.